In this section, we'll look back to ACI 530-11, the same code we were using for analyzing the ramp walls as compression struts in the previous section, but this time we'll look for out-of-plane flexural capacity and shear capacity in section 2.2 for unreinforced masonry. We are first directed to table 2.2.3.2 for out-of-plane bending, and here for loads normal to bed joints, Portland cement, and solid units in running bond, which are the assumptions we make, we read a required capacity of 53 psi to be our, so that would be our FB, or our capacity. As a sanity check, another method for calculating capacity is just to take the 1/3 of the masonry compressive strength, so F prime M over 3, and remember that is 1.5 megapascals, and that converts to 72.5 psi, which is a conservative estimate for flexural capacity. So that's just confirming as a sanity check that 53 psi is good to use moving forward. Now, from this diagram here, the maximum moment of the wall section will be equal to the overturning moment calculated above, or in this case 0.54 kilonewton meters per meter. Per meter of wall. And to calculate the demand load, we'll divide this by the section modulus. And the section is illustrated here where B is the shortest wall length from the anchor to the foundation, but we'll just take this as 1 meter. Remember, because we're doing this per 1 meter of wall, and H is actually the actual width of the wall, so that is 30 centimeters in our worst case scenario analysis. So we have our section modulus calculated from our moment of inertia is BH squared over 12. We have our then flexural stresses to be M over S, or our overturning moment over our section modulus, and our factor of safety to be our capacity of 53 psi over our stresses, which we'll find to be about 5. So we're good. Now for shear, similar to the compression strut check, we'll check condition C, assuming no compressive load is occurring. So there's no addition to capacity here, that NV term from the compression strut check. We'll have our stresses to be 1.5 V over A, where V, the shear, is just our P rock plus P grout terms added, and our area is our B times H, with B once again being taken as 1 because we're doing this per meter of wall. And we can calculate, we will check that our FV is less than or equal to 37 psi from condition C, and we'll get 1.31 is, for our worst case scenario, is less than 37. So the conclusion here is there will be an obvious addition of capacity from the strength of the wall. However, there are many factors and unknowns throughout a build that can't truly be accounted for by a general check like this. How much wall is built before the fill, the embedment of the wall in the soil, the workmanship, the height of the walls, the time to cure before being filled, and much more. So therefore, using our worst case scenario check from before, and assuming there will be some capacity from the soil if it's at ground level, or some capacity from the actual strength of the wall as we move upward, we'll recommend a maximum of 1 meter rise per day in ramp fill. And this is also pretty reasonable to actually, raise the ramp fill so you can work on the ramp walls as they get higher. If you wish to fill the ramps greater than 1 meter per day, a site-specific calculation should be performed considering some of the other forces that are going to be occurring in this situation. And that will conclude our ramp wall stability checks that are really just a background for our general rule that we reported in previous lecture.